Hi, welcome back to this new video. This is going to be an interesting one wherein we will be constructing the SFD and BMD for four different beams. Okay, the first one is a cantilever beam. This that we see here. Here this acted upon by two concentrated loads and then two concentrated moments at these locations B, C, D respectively. The first step is to determine what the reactions, right? One can easily do it here. One can see that the vertical reaction here is going to be zero, whereas this clockwise reactive moment at this joint A is going to be 40 kilonewton. One can easily find that. All right. So what one should do afterwards, after this first step, one can straight away start drawing the SFB. All right. So we see that there is no reactive force here. So this should start with a zero, and between here it should start with a zero. And in this segment of the beam AB, we don't have any other force acting, therefore it should remain a straight line, right? Now, what should happen at this point B? You have a concentrated force acting here. In our previous videos, we have shown only the loads which are uniformly distributed, right? Here we are seeing that there is a concentrated load acting here. So what should happen here is there should be a jump discontinuity here, okay? Because what happens is if you differentiate the ordinate of SMD here, it can be related to what we call a direct delta function. Okay, that's how it goes. So whenever you have a concentrated load at the corresponding location in the shear force diagram, there should be a jump, okay, which is the jump discontinuity, right? And this height should be equal to the magnitude of concentrated load acting at that location. Okay. Okay, proceeding forward, and then if we consider span BC, you don't have any other force acting in between, even though you have a concentrated moment acting at this location C, however, it is not going to affect the SFB. Okay, it is going to have influence only the BMD, which we will subsequently see now. Fine. So between this location B and D, you don't have any other force acting. Therefore, this should remain constant within this region. That is, the SFD coordinate should remain constant. So finally, when it reaches the free end, you have this force 10 kilonewton acting, which is upward, right? For us, we know that the force which is acting upward on the right face and which acts downward on the left face forms a positive shear force, right? Constitutes a positive shear force for us. So this should end with this positive ordinate here. That's how we finally finish this shear force diagram. Okay. Next, we are going to draw the bending moment diagram. So here we see that we have 40 kilonewton meter clockwise reactive moment here. Therefore, it should start with this 40 kilonewton meter ordinate, which is positive here, right? And then between this point A and B, you don't have any other concentrated moment or any moment as such, or even forces acting. Therefore, it should remain a straight line. All right. So now between this BC, what should happen? It has to be a straight line with a constant slope. Why? Only then you can relate the slope to the corresponding ordinate of shear force diagram in this segment BC. Okay. So if this is positive ordinate here, the slope should be clockwise, which is negative for us. Okay. And what should happen at this point C? As I told, if there is a concentrated load acting, there is going to be a discontinuity, jump discontinuity in the shear force diagram. In the same manner, if you have a concentrated moment acting anywhere in your beam, at that location, you are going to have what? A jump discontinuity in the bending moment diagram, okay, because of this concentrated moment happening here, okay, occurring here. So, and this values should be equal to the magnitude of concentrated moment acting at that location, fine. So, you have to find what is that value. One needs to draw the free body diagram of this portion, and one needs to see what is the value of bending moment at the left proximity of this point C, and then to its right proximity. Okay, now to do that, one should draw the free body diagram as we see here. So from this we can see MC minus equal to 30 kilonewton meter, and then if we consider the equilibrium condition of this joint C alone, one can determine that MC plus is going to be 20 kilonewton meter. Okay, so this is 30 kilonewton meter and this one is 20 kilonewton meter. This therefore tells us that from here it has to come down to 20 kilonewton meter as we see here. Okay. And finally, at the right end, at the free end, we have this clockwise 10 kilonewton meter constant moment acting here, right? So we should see a jump discontinuity here, and also it should end with the ordinate corresponding to this concentrated moment acting here. Mind that this is a clockwise moment, but for us, this constitutes the positive moment, right? So because we have a clockwise moment here, it should be related to a negative ordinate here, right? So that's why we see this is 10 kilometer an hour. Therefore, it has to come to the other side. Okay, and it has to be a straight line. Fine. So that's how we finish the minimum diagram for this case. Hope it makes sense. Now we will move on to the second problem. Here we have span AB, BC, and CD, wherein we have different uniformly distributed loads acting. For the span AB, we see that we have a uniformly varying load acting downwards, and for the span CD, it is uniformly varying load but it's acting upward. And in the span BC, we have a uniformly distributed load acting, which magnitude is 1 kilonewton meter acting downwards, right? The first step is to determine the support reactions. So one can directly find out what is the reaction at this point and this point, which are given here. Okay, one can verify that. Now we need to consider segment A, B, B, C, and C, D separately. Why? Because you have a different kind of loads acting on each of this segment, right? So if we first consider the span AB, one should start with first the reaction at the left hand, right? So the reaction is here 73 by 24, which is upward, right? So if it is left hand and it is upward, it should mean a negative ordinate to us. So one should start with this negative ordinate here. Now when you reach point B, you should also know what is the value of the shear force at this joint B. Okay. Only then you can say whether it is going, like, I mean, one needs to determine what is the height also. Okay. So in order to do that, one is this value and see that you have this negative one which is gradually increasing from the left hand. Therefore, this pattern should be like this. Only then you can relate this positive slope which is gradually increasing from the left hand towards the right hand to the corresponding negative ordinates here. Okay, so that's the way we determine this variation here. Now in order to know this value, and also you can see that it's attaining a zero value here, right? So one needs to find this location as well. Why? Only then you can find the maximum bending moment. Okay, so the location where the shear force diagram crosses zero is the location where you see the local maximum bending moment. So one needs to determine this value as well as one also need to find this value. Okay, now to do that, we are going to cut a segment here from the span AB and we are drawing the free body diagram here. Okay, so one can write the expression for Vx equated to zero, then you will find this location where it is, I mean, the shear force is becoming zero. Okay. So using this expression, you can substitute the value of x corresponding to this. Okay, that's what I have done here to determine the value of VB, right? Now one also needs to get the expression for, one can directly consider a free body diagram. Okay, at this location, you can find the maximum minimum. I'm not doing that. What I'm doing is I'm directly getting from this Weber diagram the expression for mx, and then I'm substituting this 2.466 meter in this to get the value of maximum bending moment. Okay, I can also find the value of bending moment at the location B. That's why I'm making use of this expression here, right? So once you know the value of VB as 35 by 24 kilonewton, one can fix this height here. So this part is done first of all, right? Now between this span BC, you have this uniformly UDL, right? Therefore, this has to be a straight line with a positive slope. Only then you can relate it to this UDL, which is negative, right? And finally, you see that you have a support reaction here, so there should be a jump discontinuity in the shape of diagram as I have told earlier. Okay, so now again we need to find VC plus and VC minus, right? So VC minus you can find from this free body diagram. Okay, what I'm doing is I'm cutting this portion alone. I'm showing here. You know already the value of VB from this free body diagram. Use that VB here. Okay. So from this VB diagram, you can find the value of VC minus. All right. Now you also need to know what is VC plus. Okay. And you may also require the bending moment, value of bending moment as location C. So I am going to take this portion, drawing the free body diagram corresponding to that portion here, from which I will determine the value of VC plus and MC. Okay. So this MC I'm going to use here for the bending moment diagram. So once you know this VC plus and VC minus, you can say whether the jump discontinuity should be which way. Okay, so you have VC minus greater than VC plus here, so it has to come down like this. All right. So after doing that, what is the next step? We need to determine the pattern for this portion CD. So this is how it has to be. Only then you can relate to the corresponding variation in the loading diagram. Okay, that completes the shear force diagram. Then let's move on to the bending moment diagram. So here we need to consider this portion separately, this separately, this separately, and this separately, because each of them show a particular pattern, right? So for this portion, this is the way the bending moment diagram should vary, right? So the slope here should be positive and it has to gradually decrease until it reaches a zero value here. Okay. So only then it can be related to the negative ordinates of the shear force diagram. Okay, that's how it is done. And then similarly, you need to determine this pattern here, which can be related to the corresponding ordinates of the shear force diagram. And when you come to this portion, you have a positive ordinate here. That means the pattern here should correspond to should be such that you have the slopes which are negative and then which should be increasing. Okay, so you can relate the slope of this portion to the corresponding ordinate here. Finally, so this pattern should correspond to this pattern should correspond to the ordinate here, positive ordinates here. Okay, so to complete this diagram, you might require this bending moment value at location BC. Okay, this you already know, right? So I have already said that MB is determined from this expression, MC is taken from this expression, and the maximum bending moment is obtained from this expression, MS. Okay, so that's all that completes the BMD for the second problem. All right. So we'll go to the third problem. Is going to be more interesting. Here we have the load in the form of sine wave. Okay. So it's going to cause a little challenge. It's going to be a bit more interesting, however. The first step is to determine the support reactions. Fine. This loading is totally downward, so the support reaction should be facing upward. And then this causes a tendency to rotate the clockwise direction. Therefore, the reactive moment should be counterclockwise here. So that's what is shown here, upward and then counterclockwise. So now, in order to determine the reactive force, you need to integrate this intensity of load given here. Okay, so the span is 6 meters, so integral 0 to 6, this expression dx, from which you will get the value of RAYS 120 by pi kilonewton. The next step is to determine the reactive moment. So this q of x into x dx integrated from 0 to 6 will give the value of the reactive moment as you see here. Okay. Then the next step is to get the expressions for bending moment and shear force. So in order to do that, I'm going to take a portion, okay, cut somewhere here. You see the free body diagram shown here. Okay. The reactions are taken from here and used here. Now you mark the positive sense of shear force bending moment at the right phase, from which you can determine from the equilibrium conditions, the expressions for Vx and Mx, right? So for Vx, you state that sum of upward force is equal to the downward force, right? 120 plus 120 by pi plus Vx should be equal to integral this dx, okay, integral between 0 to x, okay, that's from which you get the expression for Vx. Now, in order to get the expression for mx, I am taking sum of motor boots, point A equal to 0. Okay, that gives you this expression. When you simplify it, you get the expression for mx. Now, we are going to use these two expressions to plot the SFD and BMD, right? So, I have used those two expressions to draw this variation of SFD and BMD. However, uh, you can relate the slope of this SFD to the corresponding ordinates, because dv by dx equal to minus q and dm by dx equal to minus v. Okay. So you can see that at both ends, this should remain flat. Only then you can see the slope is related to the zero ordinate here at both ends. Now, throughout this variation, you see that the slope is going to be positive. Okay, for us, the counterclockwise slopes are positive, right? You can see that throughout this span, okay, the slope is remaining positive. However, the variation is such that it attains gradually a maximum value here, and then it gradually reduces towards the free end. And at the midspan, you see that it attains a maximum value. That is, you see that the slope of the tangent drawn is steeper here at the midspan, which corresponds to the maximum ordinate here, right? Similarly, you can draw the minimum diagram. Okay, you see that this ordinate is throughout uh, negative, and this is gradually reducing, and it's becoming zero at the free end, right? So this nonlinear trend should be such that the slope is positive, but it keeps reducing until it attains a zero value at the free end. Okay, that's how you can relate this SFD and then the BMD. Okay, we have finally different beam, which is statically determined. You have four unknowns, two here, one here, two plus one plus one, which is four, two static equations of equilibrium, and then two equations of condition due to the presence of internal releases here. You have a shear release here, and then you have a moment release here. So you can watch our previous videos wherein we explained how to determine the reactions. Okay, so you can find these reactions here, which are shown here, and then you can also draw the free body diagrams from which you can see the values of you have a moment here, bending moment here, and you have a shear force here, right? So those values are given here, right? But I am not going to explain this entirely. I'm just showing the variation. Okay. If it is clear from the first three problems, you can easily draw this SFD and BMD. I'm not marking the values as so also here. One can try this and one can tell whether this is right or wrong, and can also tell what are these values here. Okay. Okay. So this is left as an exercise. So you can take these values here. Okay. And then one can construct the SFD and BMD. And I'm also showing the deflected profile, which is interesting. Okay, one can also check this here. So as you have a shear release here, this gap is seen here. Okay, this is a fixed end, so the slope of the deflected profile is zero here. And then you have an internal release here, which means you should have a slope discontinuity in the elastic curve here. All right. So you can check this deflected profile as well. One can relay this deflected profile to the bending moment diagram. Okay. One can do that and comment in our video. Hope this is helpful. Thank you so much for watching. We'll see in another video.